Great. Welcome back to the HoTT, the Homotopy Type Theory Electronic Seminar Talks. Today, we're very happy to welcome Omar Antolín Camarena, who is going to tell us some hot lessons for algebraic topologists.
Thanks, Emily. Thanks a lot for the invitation. Well, thanks to, I guess that's more specifically thanks to Chris, who invited me, but thanks to all the organizers. So I was a little bit surprised I was invited to the seminar since I do not work in homotopy type theory, but as at least Emily and Chris know, I'm interested in it, and I like thinking about it. I don't know that much about it, but so I thought I could come here and give sort of an outsider's point of view, tell you about some of the experiences I've had learning homotopy type theory, and particularly some styles of arguments and some ways of thinking about homotopy theory that I think are more common in homotopy type theory than outside it, and that there's no reason they have to stay confined to homotopy type theory, and it's a useful way to think about homotopy theory in general. I put this quote from Alan Kay on the title page, which is the only prepared slide I have. It's going to be like a chalkboard talk. So Alan Kay was a computer scientist who worked at Xerox in Palo Alto, and when they developed like the first graphical user interfaces, and I think even the mouse was invented there, but certainly the concepts of windows on a computer screen and clicking on things, and so he's very influential in computer science in general, object-oriented programming, and he'd like to say that having the right point of view is worth 80 IQ points. And I don't want to endorse using IQ points to measure anything, but the sense of the quote is pretty clear, right? Having the right point of view on things can enable you to do things much easier than you could otherwise. So the main habit that I think that general homotopy theorists could import from homotopy type theory to great profit is just the willingness to use the universe. And so from my point of view, the universe, I just mean, so the way I think of it in terms of just infinity category theory is, of course, as the maximal groupoid in the infinity category of spaces, the classifying space for all spaces, I guess. And that's just a disjoint union of classifying spaces of automorphism, of homotopy self-equivalences of spaces. I guess your X ranges over homotopy equivalence types of spaces. And of course, there are size issues that everyone is aware of. And I don't think that those in general are actually confusing. And so this space is something that's, of course, available without homotopy type theory, but different setups have different affordances, and they make different things easier and natural to, and it's not, some of it is intrinsic, some of it is just cultural, but people used to different languages and different ways of expressing will find some thoughts more natural than others, and will tend to do certain things more often than others. And in homotopy type theory, it's just extremely natural to always use the universe, thinking of type family, of course. And and in more classical terms, as you're all aware, something like this you can think of as a map from some other space, maybe I'll call it B tilde, to A, and the relation is that B of A is given by the homotopy fibers of the other map. Right? And so this B is, so if I think of this as infinity categorically as a functor from A to spaces, this is the Groton deconstruction. In homotopy type theory, it is called some type corresponding to this type family. just going back and forth between these things freely is something that I think should see more use in homotopy. And so here I should pause to explain what I meant by algebraic topologist in the title of the talk. I guess I don't really mean sort of traditional classical algebraic topology done, with ordinary category theory in the category of spaces and where things like vibrations and so on become important. I don't think many of the ideas in homotopy type theory that I want sort of more general homotopy theorists to start using are really that easy to import into a more classical way of working. I think what I really meant by algebraic topologists is people that approach algebraic topology in sort of in a fully homotopical way of thinking. And maybe the most practical way to do that nowadays is through the theory of infinity categories. And so people that are already working in that mode can easily import almost any idea from homotopy type theory, I think. And the point of this talk is that there are some habits that they could use that don't see that much use. It would be good to start using them more because it really clarifies them. And you can also think of it the other way around. The theory of infinity categories is still a little bit it's still a difficult theory to get into, and there are a lot of promising. The exposition of the fundamentals of the theory is being simplified all the time now, and homotopy type theory is probably a good way to get into that way of thinking. And so I think here I'll illustrate. I'll use sort of infinity categorical language that I'm comfortable with to explain ideas you already know from homotopy type theory. And I think this is the setting in which I say that people that are not in homotopy type theory but do work in homotopy theory with this language can easily import ideas from homotopy type theory. So let me give some examples of the use of this ideas. One nice example that I liked a lot is computing the loop space of the circle, right, as is done in homotopy type theory. So for purposes of doing this, well, you need an appropriate definition of the circle. And here, so in homotopy type theory, you say it's the higher inductive type generated by one point in one loop. I guess a more categorical way to express that is that it's the homotopy co-equalizer of two copies of the map from a point to a point. And screen seemed to stop updating. Right. So then, if you want to compute the loop space of this, well, you want to do a homotopy pullback of this shape. And the point is that you can use, so S1 here is defined through as a homotopy colimit, and so it has a universal property for maps out of it. And using this idea of a type family, you can use a universal property for maps out of A to describe maps into A, right? And so the strategy that I read in the homotopy type theory book for computing the loop space of S1, which I thought was very neat, was, well, you say what you think the universal cover should be, and then just prove that it is, right? And so here, the way this argument goes is that I want to describe the universal cover of S1. That is a map into S1, but I can equivalently describe it as a map from S1 to the universe. And for this, I can use the fact that S1 was defined this way to describe this map in different terms, right? Since it is the homotopy co-equalizer of maps from point to a point, This means that giving a map like this corresponds to giving a pair of spaces and two equivalences between them. Oh, there. I hope the screen will eventually catch up with what I'm writing. Maybe sorry for this technical difficulty. Why is this not up? Let me try stopping it and starting it again. Okay, that's better. So because it's defined as homotopy co-equalizer this way, giving a map into the universe means giving 2 points of it, that is 2 spaces, and then 2 maps inside here, so 2 equivalences. And of course, you know, when you have these 2 equivalences, you get a self-equivalence of X given by just composing one with a homotopy inverse for the other. And really, if you had this, you could just take Y to be X, take one of these to be the identity and the other one the homotopy self-equivalence. So it's really just a matter of giving one space and a self-equivalence. And so then the one you want to build is the one that corresponds to just the discrete space of integers and the self-equivalence that that just adds 1, right? And so then this is a model for the universal cover of S1. And what you want to show to compute so if it really were this, if, for example, the sum type corresponding to this, you could show is contractible, that would imply that then this is this homotopy fiber, right? So that would tell you, and I kept saying the universal cover because it is, but what I really want to get at is not just that this is some simply connected space, but that it's in fact contractible, because that way you're not just getting a computation of the fundamental group, but you're getting a computation of the entire loop space. And oh boy, I thought this was going to be more reliable. I've given a talk like this before with 0 difficulty. Okay, try again. I hope this doesn't keep happening, right? So, okay. So how do you show that this is contractible? Well, in the end, what you have to do is just, what flattening tells you is that this total space of the fibration, you could think of it as the same diagram upstairs, right? And so here, remember, I use this language to describe this in more familiar terms, but remember this correspondence here. What you get is that you want to compute the homotopy co-equalizer of the identity map and this map here, the one that adds 1. And computing this is, well, now this is something that's a pretty standard exercise in just homotopy co-limits. You could, if you're thinking sort of more classically about this, you just draw the picture, right? You have Z, and then every point is joined with an interval to its successor. So you get the real line, which is contractible. So here I'll even say that, with the correct model of, with some appropriate fixed formula in spaces for computing homotopy co-limits, you actually just get a space homeomorphic reals, and that is contractible, right? So, okay, so this is the calculation in one of the ways to calculate in homotopy type theory, the loop space of S1. And here, the point I want to make is exactly that the power of of the universe here was to be able to build vibrations over a space that's defined as a homotopy colimit by saying what you want the fiber above the pieces to be and what you want the maps in the diagram to correspond to, right? This is what in homotopy type theory, the fact that those two things are equivalent, I guess, is what it's called flattening. And so this is a useful perspective, I think, because it's often, this is one of the easiest ways to define maps into something defined as a homotopy colimit, right? Normally what I would do is, so often a good way to do this is to, define another diagram of the same shape and a natural transformation between them, and then take homotopy colimits. And that's a style of argument that is often equivalent to this. I'm just saying that flattening suggests that mode of arguing very directly. And just what I find funny about this idea that maps into a space correspond to maps from it to the universe is that it is perfectly available. It was already available to me before I read any blog posts about homotopy type theory, but I did find myself using it more afterwards, right? And if you're willing to think not just about homotopy types, but about infinity categories, that broadens the scope of this idea a little bit, so that you can also use categories in your arguments, thinking of spaces as infinity groupoids. And let me give you an example of that. I want to use this in a case where I don't, where there's something that I want to use that is real, that is really a category, or an infinity category that is not an infinity groupoid, or it has objects that are complicated to define. Let me just give you the example I have in mind. So you can, oh, sorry. Wait, before that example, there was one more thing of this kind that is standard in homotopy type theory that I wanted to mention as an example of this phenomenon, and that is the theory of covering spaces. And I like the homotopy type theoretical version of the theory of covering spaces because I think it has a second lesson beyond just use the universe. Often don't be shy about converting maps into space into maps to the universe. This covering spaces story has a different lesson in addition to that, which is that if you're only doing homotopy theoretical things, you can often settle for homotopy theoretical statements, and those can often be given a purely homotopy theoretical proof, right? So the classical theory about covering spaces is not about homotopy types, right? It's about actual continuous maps between topological spaces that are locally homeomorphisms, and the base that has every point in the base has an open set around it that is evenly covered by this map I, right? So the pre-image here, it becomes a disjoint union of copies of UI, and I restricted to each of these is a homeomorphism. And sometimes you need the full power of this, and sometimes you don't. It depends on what you're doing. If you're interfacing with other areas of mathematics like differential geometry, or I guess that's the main example. Sometimes you really want these things to be actual homeomorphisms of actual spaces that are not homotopy types. They're determined up to homeomorphism. But for some purposes, you don't need any of this, right? If you want to talk just if you're doing later some homotopy theoretical calculation, you want to compute some homotopy groups or something like that, often you don't need exactly a covering space, and you would be able to get away with, I guess, the homotopy theoretic version, which I'll just call a homotopy covering space. And that just means map with homotopy fibers that are homotopy discrete. And I won't write the word homotopy. Now, the natural definition in homotopy type theory is this relaxed notion of covering space. Sorry, that. This is the sort of native notion of covering spaces in homotopy type theory. But the nice thing about it is that, yes, if you classify these kinds of covers, you don't get the same kind of statement about these maps that are, actual continuous functions between spaces that are locally homeomorphisms in this way. But on the flip side, proving the main results about covering spaces becomes easier using the universe, right? So if I have a map with discrete fibers, well, I can regard that as it's a map into X, so I can think of it as a map into the universe. But the fact, and in this correspondence between maps into X and maps into the universe, this sends each point in X to the homotopy fiber of the map above it. So what we're saying here is that this factors through the type of sets, right? Which I will write this way because I usually use set for the category, right? And so this is here, the type of sets is of course just the disjoint union of the classifying spaces of the symmetric groups for all sets. Here, X ranges over one set of each cardinality, and of course, as usual, you have to pick where to stop, right? Just anywhere big enough to contain all the fibers. And so, if you're
using X in two different ways as a space.
Oh, yes, I am. This one is locally bound, but it's probably still a good idea to change the name. Got into a computer state of mind where like this binding just doesn't see the other one. The compiler wouldn't complain. Right. So so you have this very nice definition of homotopy covering space, which is just a functor from X thought of as an infinity groupoid to the category of sets. Because X is an infinity groupoid, this automatically lands inside the maximal groupoid. And I like thinking about it this way just because I'm more used to talking about the category of sets than the type of sets. And so what's nice about thinking of a covering space this way by its classifying map is that now you can argue that since in set the mapping spaces are discrete, then this automatically has to factor through the first Posnikov truncation of X, right? So any functor from X into sets, or any map from X into the type of sets, it automatically factors through the first Posnikov truncation of X, right? And so we get that coverings, the category of coverings of X, that is equivalent to functors from X into set, but that in turn is equivalent to just functors from the Posnikov truncation into set. And the Posnikov truncation, its algebraic version is just a fundamental groupoid. Right? And so you directly get this main theorem in the theory of classifying spaces, of covering spaces, that to give a cover is the same as giving a representation of the fundamental groupoid, which by definition just means functor. And further, you can do, if you really wanted just the fundamental group, well, now it's clear when that works. If X is connected, then the fundamental groupoid is equivalent to the fundamental group thought of as a one-object category. So its category of functors into anywhere will also be equivalent. And so you get this main theorem just very directly from noticing that here the mapping spaces are discrete. And this is essentially how the development of the theory of covering spaces is done in homotopy type theory. And so I think this really shows like a second habit that I've tried to adopt. And maybe in this case, actually, since before I noticed that this is what happens in homotopy type theory. But yeah, think if you're doing something purely homotopy theoretical, there's lots of unnecessary strictness in sort of traditional topology that you don't always need. And sometimes if you're satisfied with a weaker homotopy theoretical statement, you can give an easier purely homotopy theoretical. And of course, this is also another example of just how comfortable it is to use the universe for maps into the universe to describe maps into a space. So the next example I wanted to talk about is homology with twisted coefficients. And so here, so I guess I'll start by giving a definition that uses this style of thinking. To give a system of local coefficients on a space X, a local system of abelian groups, all you need to do is give a functor from X, thought of as an infinity groupoid, into the category of abelian groups, right? And I think I might need some space on top. And if you want to compute the homology of this, you just compose with the Eilenberg-MacLane functor that gives Eilenberg-MacLane spectra for an abelian group. This lands in the infinity category of spectra. And then the homology of X, maybe homology of X with these twisted coefficients, you can just define it as the homotopy groups of the colimit of this composite. Okay, and that's a nice succinct definition. Let me prove one thing about it. So as to illustrate that, it makes it easy to reason about this. Again, this is an ordinary category. So here again, mapping spaces are discrete. So again, this factors through the groupoid I get by taking the zero truncation of the mapping spaces in X, which globally in terms of all of X means taking the first Posnikov section as before. And so this is another example of the same thing we saw in covering spaces. So any functor like this just automatically factors through the first Posnikov truncation, whose sort of purely algebraic avatar is the fundamental groupoid, right? So this shows that these local systems of abelian groups on X are really the same thing as representations of the fundamental in abelian groups. But the nice thing about using F instead of this restricted F bar is that it allows you to give this definition of the homology with twisted coefficients. And, you can try to stay in spectra as long as possible and only take homotopy groups at the end. I think this is another habit that is something that you gravitate towards naturally in homotopy type theory, which is decategorifying as late as possible, right? So if you're working with, so here I involve spectra, but let's just go think about homotopy types of spaces, and you want to do some sort of calculation with them. I think that the tools in homotopy type theory encourage you to stay with the entire type as long as possible and delay operations like truncation or computing homotopy groups or so on, and just most of the time argue with the full homotopy types. And it just sort of the tools available to you sort of push you in that direction, I find. And classical arguments will sort of start writing long exact sequences in homotopy or long exact sequences in homology right away. And yeah, this is sort of a vague feeling that I get from reading a bunch of stuff, both classical and in homotopy type theory. I like this idea of holding on to the information as long as possible, and then at the last step, extracting homotopy or something like that. So this decategorifying as late as possible, I find it's useful because it clarifies at which level each constructions really belong. And it's one of those things that I think just the affordances of homotopy type theory push you in the direction of doing pretty naturally without you noticing. Right. Okay, so what can I say about homology with twisted coefficients? So one thing we could do with this information that a local system automatically factors through the fundamental groupoid is to relate this to homology on the universal cover. The homotopy fiber of this map to the canonical map to the one truncation, that is the universal cover of X, right? And so let me call this map P. If I want to compute the colimit of a functor out of X, like H composed with F, and again, here I'll save decategorification for later. I'll just compute the colimit and then we'll, and at the end, just apply pi star everywhere. I'll get a statement about this spectrum actually, right? So to compute a colimit like this, trick that is, oops, sorry, I lost connection. Let's see if it reconnects automatically. It's been stable for a while. One trick that I'll start writing it and then explain when things come back online. It's helpful. Sorry, let me. Okay. All right. So, what I was going to say is that a technique that is often helpful to compute colimits is that if you have a functor that is a co-Cartesian fibration, well, before that, if you want to compute the colimit of a functor f, that is the same thing as left con-extending along the map, the functor from A to the terminal category. So I could take QP, the left can extension of F along QP, and that is one way of computing the colimit, right? And so here I factored this canonical map to the terminal category through a co-Cartesian fibration. And you don't need to know what these are, but if A and B are infinity groupoids, then any map is a co-Cartesian fibration. So this is if I'm computing colimits where the shape is a space, this is a trick. The trick I'm explaining now, which I should finish explaining before probably, is one you can always use with spaces. And so the trick is that here you can just do this in two stages, of course. You can first left conextend along P and then left conextend along Q. And so this, of course, just means taking the colimit of the left conextension along P. But the nice thing about left conextending along a co-Cartesian fibration is that to compute this conextension, all you have to do is take colimits along the fibers, right? So you have the fiber, maybe I'll use the usual notation in homotopy type theory, which is take the fiber of P at B, and I can compose with F to get a functor into E. And this describes the left conextension along a co-Cartesian fibration. And so this is a trick that you can always use for spaces. And so here, what this tells me is that I can compute this as the colimit of the left conextension along the map to the first Postnikov truncation of H composed with F, right? And this functor, what does it do? This functor right here, move this down a little bit. Well, this functor sends a point in the truncation to H composed with F of the fiber. Okay. And sorry, that's not what I meant to say. Sorry, so this functor, what it is the functor that sends X to the colimit, sorry, that's what I meant to say, of the fiber of this projection. Mapping into spectra via a restriction of this functor H composed with F. Now, the fiber here, that is the universal cover. Let's say that X is connected. So I don't have to, I guess it's the universal cover of the component in which X is, but let's just think that X is connected. This is the universal cover. And the point here is that H composed with F restricted to the universal cover, this composite, H composed with F composed with pi, that functor is constant, right? Pi composed with F is constant because F factored through the first Postnikov truncation. So if I do pi and then F, that is the same as doing pi, then P, then F bar. But pi followed by P, that is homotopic to the constant map, right? Because the universal cover is the homotopy fiber of P, right? So this functor, this composite here is homotopic to a constant map with value some abelian group A, right? And so here I'm taking the colimit of a constant functor on the space X bar. What I get is that this colimit is just the result of the tensoring of spectra over spaces applied to the Eilenberg-MacLane space of this constant group A that this composite is homotopic to, right? So this is, if you want to regard, this is, since this is an HZ module, this whole thing is an HZ module. And if you think about the equivalences between HZ module spectra and chain complexes, this is chains on the universal cover. Okay. tensored with A. Well, let's just say, let's call it chains with coefficients in A. Chains on the universal cover with coefficients in A. And so that is the functor here whose colimit I'm taking. And now this colimit is over just the fundamental groupoid, and I'm thinking of the spaces connected. So this means just taking the colimit over the fundamental group of X, which means taking homotopy orbits of the group action. So altogether, this colimit here works out to be this spectrum, which corresponds to chains on the universal cover with coefficients in A. And here I take homotopy orbits for the action of the fundamental group, which acts on diagonally on this tensor product, right? It acts on X tilde by deck transformations, and it acts on A the way F bar indicates, right? F bar is a representation of this fundamental group on the abelian group A. And so this is one of the traditional ways of defining homology with twisted coefficients as just, the homology groups, the homotopy groups of this spectrum, which people usually regard instead as the page is getting a little bit crowded. So what we got is that homology X with twisted coefficients F, we could think of as homotopy groups of. Okay, so right, so this doesn't seem to work. Okay, so what we did on that last slide with the sloppy board work, sorry for that, all over the place, is relate this sort of, oh, there it is. I can share again. So what we did here was show that if you define homology with twisted coefficients using this idea of taking a colimit with of a diagram whose shape is the entire space X, you can use the same trick that we used that we used for covering spaces, of noticing that since this middle category here, the category of abelian groups, has discrete mapping spaces, a functor into it from X automatically factors through the first Posnikov truncation, right? And then using this trick of computing homotopy colimits by first left con extending along a co-Cartesian fibration that has a special property that it's easy to compute. You just take colimits along the fibers. This intermediate step often simplifies a colimit. You can take the colimit of F, you can compute the colimit of F instead as the colimit of the left con extension along P, which has this easy description. So using that here, what we saw is that this spectrum whose homotopy, the spectrum whose homotopy groups are the twisted homology, that spectrum, if I compute it by first left con extending along the Posnikov truncation map, there the fiber is the universal cover, and I get colimit of the composite of this functor to spectra with the projection from the universal cover. And then I argued that on the composed with the projection from the universal cover, this local system actually becomes a constant functor, just because it factored through the Posnikov truncation. And so then you get a nice easy formula for the left con extension. And then taking the colimit of that just means taking homotopy invariance for the group action. And if you relate that to chain complexes and look at how strict you can get away with using models, you'll see that you have chains on the universal cover the action of the fundamental group there is free, so you don't really need to take homotopy orbits. You can just take the usual group quotient and the usual quotient by the action of the group, and then you get one of the traditional formulas for homology with twisted coefficients, which I wrote down expecting that maybe it'll appear on the screen at some point. There it is, right? And so then if you look at this spectrum instead as a chain complex, it's integral chains on the universal cover tensored with A. Okay, so I think I'll give up on this. But so other, I think that's basically the examples that I wanted to show. And so this last example is still something you could do internally to homotopy type theory. You would just, it would feel only slightly less natural in that you would replace the category of abelian groups with the type of abelian groups. And, you know, I'm just more used to thinking of the category, but there's nothing wrong with taking the maximal subgroupoid, and that is something that you could directly talk about in homotopy type theory. And spectra, well, you'd have to build spectra, but again, you can take you know, the maximal subgroupoid of the infinity category of spectra. That would be the type of spectra. That has certainly been described in homotopy type theory. And so, you know, I'm not personally familiar with what this lemma that says that you can take the sum type by first, if you, by taking an arbitrary map, then summing first over the fibers of the map and then summing the fibers, right? But that's probably something that's easy to prove in homotopy type theory. I think of it in terms of these left com extensions along co-Cartesian vibrations, but in a sense that's more complicated than necessary because I was only dealing with infinity groupoids anyway. Right? And what I like about this last example is that it uses the same idea of describing vibrations by their classifying maps in a setting where you don't really have the total space of the vibration, right? The total space of that vibration would be something with a map to the space X, but where the fibers are spectra. And you can try to build a framework where that makes sense, or you could just never take the total space, which is a lot easier. And I was introduced to this point of view when thinking about Tom spectra. There's this point of infinity categorical point of view on Tom spectra developed in a paper by Ando, Blumberg, Gepner, Hopkins, and Resk. And I've done some work on that. Toby Bartel and I have a paper on the universal property that the multiplicative structure of the Tom spectrum satisfies. And there, I really appreciated the idea that, you know, you can deal with bundles or vibrations through their classifying maps, even in settings where it's awkward to make sense of the total space. And this again is, I think this is, in the case of Tom spectra, this turns out to be a great way of looking at them and makes a lot of things very natural. And again, it's a way of thinking that I think homotopy type theory would push you in the direction, right? If you stick with just maps to the universe, well, then you might not realize that you just sometimes never need to take the dependent sum, right? If you're used to going back and forth between the family of types and the map from the sum to the base, you might not realize that, you know, for many things you just need the type family, but I don't think that's actually what happens, because I think from what I've read in homotopy type theory, people really find thinking of these type families very naturally, and they only sort of, that is the fundamental thing, and the dependent sum is something that you can compute out of it if you need it, right? From a more classical point of view in algebraic topology, I don't know, I was using the turning things into vibrations as sort of a safety blanket. And I think what really pushed me to get rid of that was thinking about Thom spectra, where there just was no total space, right? Because this was a vibration whose fibers were spectra. And so again, this is another thing that I don't think I learned this particular lesson through homotopy type theory, but I could have, right? I think it's another thing that homotopy type theory pushes you towards. And finally, I wanted to say that there are some other aspects of homotopy type theory that I find very intriguing, and I find that there are sort of different ways about thinking of things that I don't know if they are actually useful. And so one thing that, for example, that there are some things that I feel are probably just due to the interest in being in formalizing things, right? So, for example, the difference between judgmental equality and paths is something that I just think is probably not relevant to informal mathematics. It's an artifact of having a formal theory, and so that's one distinction that I find intriguing. But I also don't think I will ever need to make that distinction sort of working informally. And that's a clear example of that. But there are some things where I'm not sure. So, for example, path induction. That is something that I don't know exactly where to place, how to think about it. It seems like it's a technical device that you both need and can exploit a lot in homotopy type theory. But it involves distinguishing between a space and the space of open paths in that space, which are homotopy equivalent. And so I'm not sure that it's a distinction that you can get a lot of mileage out of working more informally. Some of the things you do with path induction, like so for example, I described this calculation of the loop space of S1. Formally proving that involves defining some maps, and those maps are defined through path induction if they go out of the path vibration. But so it's something that I'm not sure it really corresponds to critical distinction working informally. But the main thing that I find very intriguing in homotopy type theory, and I don't know if it's something that I could benefit from thinking about outside of homotopy type theory, is that many things have sort of a more dependently typed universal property than the universal property that I would write down just thinking categorically, right? And so often these more dependently typed universal properties, this is maybe something where it would be useful to write down an example. So one I was thinking of particularly is the universal property of the truncation, of the Postnikov truncation. So there, the universal property that I would write down is just that maps from X to an n-truncated space Y are the same thing as maps from the truncation of X into Y, right? But there is another universal property that the truncation has in homotopy type theory, which is sort of a fiber-wise version of that, right? It says something like, if you have, so I'll describe it in terms of vibrations. If you have a vibration over the n truncation of X, where the fibers are again n types, and you have a section of that vibration on all of X, it factors uniquely through a section on the n truncation. That's sort of a fiber-wise version of the other universal property. And these things that are more dependently typed, and I think usually the relation between the more dependently typed version and the version I would naturally write down just thinking category theoretically usually turns out to be like there is some type family that I'm thinking of as constant, but it doesn't have to be constant. And I don't know if I should start thinking about these dependently typed universal properties and getting, if I would get further mileage out of it. I don't have examples of that helping yet. And so that's one thing I would like to know. Like it seems very convenient in homotopy type theory to prove these more general statements, then deduce the sort of the ones where the family is constant as a corollary. And I think the extra structure sometimes points you in the right direction for the argument. That could be the case. But that's one thing that I don't know if it's helpful when you're working informally. I also haven't thought about it that much. And so that is sort of a question to this community. Should I be thinking about these more dependently typed universal properties more? And I think that was sort of the main example of something that I found very intriguing, but that I don't know how helpful it will be, was. Other than that, I think I got to most of the examples of habits that come from homotopy type theory that I think are useful outside of it. So maybe this is a good point to stop and start a discussion. Thanks again.
Great. Let's do the traditional silent applause.
Sorry for the technical difficulties, which drew me a bit.
I think that impacted the audience less than you think. So, all right, who wants to start with a question?
I'll start the discussion. I have lots of things I'd like to bring up, but I'll just start somewhere and let other people ask questions as well. So I definitely think that you've hit on some great points. Maybe I'll just mention, well, how about the last thing you mentioned, the dependent universal properties? That's a good one to discuss. So one example of an induction principle, which is what these are, is the principle for the natural numbers.
Mm-hmm.
That, so a non-dependent one would say that if you want to define a function from the natural numbers, you say where 0 goes, and you say if you know where n goes, say where n plus 1 goes.
Mm-hmm.
But the dependent one is proof by induction. Now you have a predicate p of n, which depends on n. And you want to prove that by proving p of 0 and proving p of n implies p of n plus 1. So the dependent one is much more powerful and useful.
Yeah.
You want the output type to be able to vary.
Right.
And I think the same principle happens for all these induction principles. The dependent ones are quite a bit more powerful. One just sort of very generic example of that is that when we state the induction principles, we don't state the uniqueness part, only the existence part. But from the dependent version, you can prove the uniqueness by taking a family of path types, which is dependent, and proving the existence of paths, which gives you uniqueness. And this is something homotopy theorists know, right? When you try to prove, we often see this thing where surjectivity in one dimension is the same as injectivity the next dimension up, because it's the existence of homotopies. But homotopies have dependent endpoints because they're between functions.
Yes.
So we definitely, it's very useful, and I don't quite have an example in an infinity category where I can say, here's a place where if you use it, it cleans up this argument. But certainly within type theory, all the time we rely on those dependent ones.
Mm-hmm. Mm-hmm.
I mean, maybe on a related topic, so this isn't so much algebraic topology, but just kind of general mathematics. I mean, I think in comparing the type theoretic sort of definition of the natural numbers with the set theoretic definition of the natural numbers, as Dan points out, sort of set theoretically, we have the principle of mathematical induction, which is dependent in the sense that, it's about predicates, which can vary, the the meaning of which will vary with n. But what really feels stronger to me is the fact that these are, in type theory, these are predicates that are valued in types as opposed to just in propositions. So, functions from n into the universe of types. And it's that additional strength that allows you to prove that two of the traditional piano axioms are redundant. So you can show that successor is injective, and that what else is true? Oh, that zero is not a successor by using this sort of structural induction / dependent recursion principle or whatever to construct some family of types dependent on n. I don't know if that was just a comment, I guess, but
yeah. I guess so is it the case that in proof irrelevant mathematics, the induction principle is actually not stronger than defining functions by recursion? I could define the function whose value on n is the truth value, the proposition P of n, and if it satisfies a hypothesis of induction, what that tells you is that if one is true, the next is true, then the constant true function is the only one that satisfies the recursion, right?
But those are valued in different propositions.
Yes,
right?
but
it's right. The dependency of the statements.
Say is that the induction principle only becomes dependently typed because you are describing the propositions themselves as types, right? And so if you standardize them by just saying some are true and some are false, then that takes values in a set, in a fixed set.
Well, but if you want this to be true in infinity topos, you're going to be dealing with infinity topos where the truth values aren't just Booleans, right? Yeah. So, so they really will be truly dependent types if you're trying to prove something in practice. Okay, I have another comment. So you asked about path induction. Yes. And again, I think that is something that traditional topologists have missed out on. So for example, it can be translated into a model category, and it's just something that's provable. You just write down some various diagrams and you can check it, but it's not a diagram that I'd ever seen written down before. I learned type theory and tried to understand this principle and just wrote it down and realized, oh yeah, that is true. But if you look at chapter 2 of the HoTT book, all these things are proved about the fundamental group of a type in these trivial ways. Where in the first algebraic topology course, how do we prove composition of paths is associative up to homotopy? We have to write down some formulas that involve some thirds and halves and so on, and all this crazy stuff. And what we now know is none of that matters. You have to once prove the path induction principle, which you can prove sort of by hand in that setting, and then you can just keep using it over and over again. Again, I think this would be dependently typed though, but you can set that all up, and topologists never thought about it that way. And basically, in general, it's just saying if you're trying to map out of some path space, just tell me where the constant paths go, and everything else will come along for the ride. But that's sort of trivial in the case where it's non-dependent. But I think it's again in the dependent case where it's not so obvious that you actually have some kind of fibration and you're able to get a section of it.
Yes.
Partially specifying section.
Yeah.
I mean, maybe this is related to Omar's question about the role of judgmental versus sort of typal equality, because in practice, like when you are using, in the example you brought up, when you're using path induction to prove associativity of path composition, at least the proofs I know rely on some judgmental equalities related to the way that you defined the binary composition function. So,
right.
So if you define binary composition by inducting on the left versus on the right, then you'll induct on sort of the left and versus on the right. And it's also, so presumably if you want to compile out that argument into a proof in homotopy theory, you'd have to compile out that aspect. I mean, maybe that's maybe that's in saying that the function you're constructing is a section of something that I don't know. It's not entirely clear to me.
Yeah, I mean, I also think definitional equality is not an unusual notion. We use it all the time, where in ordinary math, certain notation is defined to be other things, and we unfold those definitions. And part of a proof is unfolding the definitions. Then part is now something where there's a non-trivial isomorphism. We keep track of the difference between those two things, and it's really a fairly similar distinction.
Yeah, I guess it feels like less hinges on the distinction.
Yeah, it's definitely true that when you're trying to get a computer to understand something, you pay very close attention to which things are definitionally true, because then the computer will do them for free.
Right. That's where you get to skip work.
Yeah. Okay, and then another thing that combines these two things is, so if you believe in path induction and you believe in using your universe, well, then you want to use that your universe is univalent, so that these equivalences you need to construct are actually paths.
Yes.
And then you can use path induction to study them.
Yeah.
And then you also get a lot of mileage.
Sure.
Out of that.
Yeah. And of course, I mean, in the example of the loop space of S1, I used that implicitly. I call attention to it, but giving a bijection from Z to Z gives you a path because of the valence.
Yeah.
There's a comment in the chat. Using the simple universal property into the total space of the type family gives you the dependent elimination, at least if your universal property has a state. I don't understand exactly what that means.
Yeah, I'd have to think about it a little more, because the dependent one tells you that the result is still fiberwise.
Yeah.
So I'm not 100% sure.
Right. Yeah. When I was thinking about path induction and whether it's it's something I should start using, I did get the feeling like the only point is that it's fiberwise. It's other than that, you can just say, well, A and the path and paths into A are homotopy equivalent, so I can just use one wherever I want. It's like if you have a fibration over the path space of A, the open paths, no endpoint is fixed, and on the constant paths you have a section, then you can extend it everywhere. That's what path induction says. And if you just want to extend it up to homotopy, then you can just say that for any path you take, your section is defined as what it was on the constant path on the left end. There you get some diagrams that commute up to homotopy but don't strictly commute. So the trickiness is to get them to actually strictly commute, making everything fiberwise so that you land in the right fiber. But if you don't need that exactly, then there really is not much more to it than saying that A and the path space of A have the same homotopy type. And I'm not sure, you definitely need that this construction is fiberwise in homotopy type theory, and I'm not sure to what extent that is necessary arguing more informally, maybe you can just deal with some more diagrams only the homotopy.
Yep, could be.
Yeah.
Here's another thing that happens if you think using homotopy type theory and try to do traditional topology, which is that you can't use Whitehead's theorem, because that's not true in every model. But you read traditional proofs and they define a map, they calculate that it's an equivalence homotopy groups, and therefore there's a map in the other direction. So what you end up trying to do is actually write down the maps in both directions and prove that they're homotopy inverses to each other. And I think that's often really revealing. You can use proofs. There's often some geometry there that was never explored because you just say, oh, by Whitehead's theorem, we're done.
Right. Yeah. Yeah.
So the theory of localization is one place where that's used a lot. And you can instead write down equivalences.
Right. Yeah. Yeah, and I guess if particular argument that uses Whitehead theorem just is not true in general, that's also something you want to know.
Yeah, that's right. Yeah, sometimes you can't generalize.
Yeah. Yeah, this sort of, I guess it's related to just this constructive aspect of homotopy type theory. That also caught me off guard several times. Like I was trying to prove that the suspension of a set is a one type, and I couldn't. And I looked it up in the book, and you need equality to be decidable. That's not something that it explains why I couldn't prove it, but it I don't know, it just caught me completely by surprise.
Yeah, so if I remember correctly, that's actually open, whether it's true.
Yeah. No, let me turn that into a claim about human psychology. There's only an easy proof if equality is decidable.
So I don't know if that's true in any infinity topos.
Right. Yeah.
Anyone else should feel to jump into, because I find this interesting and want to keep chatting, but please speak up.
Yeah.
Yeah. Hello. I don't know if this is appropriate for this topic, but let me ask an elementary question. What's the pathway from taking the graduate school elementary presentation of the path space, in which path concatenation is defined, that the associativity is defined by explicitly writing the formulas for the homotopy, etc., and then proving that setup satisfies the axioms or definition of path induction in HoTT.
Do you want me to answer?
Yeah, well, I mean, I haven't thought about that.
Familiar. I've read the proofs, the easy proofs of properties like associativity of path concatenation. But they follow right away from the axioms of type theory. But how do we get from the axiomatic presentation that is traditional, which has all the complications that we can complain about, and prove that the traditional setup situation is actually a model for the elegant homotopy type theory situation?
Yeah. So the way I understood that finally was by showing or noticing that the path space has the right properties from a model category point of view. So I don't know if this will help you exactly, but you need to show that you can factorize the diagonal map from a space X to X cross X through the path space. And that the first map in the factorization is a homotopy equivalence and also a cofibration, and that the second map is a fibration. And then you can use properties of cofibrations and fibrations to show that in the corresponding problem where you've got some family over the path space, you will get a lifted map, a section. And that corresponds to what path induction says should exist.
Yeah. Specifically that the map from A to the path space, sending a point to the constant, that's a cofibration, that gives path induction.
Okay, so there.
Problem is that maybe that's less elementary.
There's a lot of, say, if you were to try to use this presentation in a graduate curriculum, there's a lot of overhead to teach people about enough category theory so they can understand model categories. Oh,
yeah. I think in this case you could get away with something focused just on this result. I haven't tried it, but I think you could say, okay, we're going to have a bit of a detour here. I have to tell you about path spaces and the property that this has, and you need to know what a fibration is. I think you can't get away from that. And then prove this result. And then I think you could just use it over and over again. I'm not saying it's the best way to do it the first time, but maybe for a second view of algebraic topology, it might be interesting.
Yeah.
I mean, at some point, so I've presented this proof in talks in topology seminars on several occasions, and it goes well if people know what a kind of monoidal model category is, Cartesian monoidal model category, and it doesn't go so well for people who don't. So you're using sort of lifting properties of the trivial cofibrations and the fibrations, but in the internal sense, so that there's some map that is then a trivial fibration, and
right.
Path induction is the section to that map.
So another comment is you were talking about families of spectra.
Yeah.
And have you thought about parametrized spectra? Because there is a world of spectra parameterized by spaces.
Yes. I think that I find it more comfortable to think of just in terms of a functor from the space to the infinity category of spectra, just because it doesn't require changing a way of thinking about these things. Like they're just functors, and I can compute colimits. I know about con extensions, and so it just lets me use tools I'm already comfortable. But certainly but it does feel like it's just a matter of convenience. Like there's not going to be statements that you couldn't just translate into the world of parameterized spectra, and all of the colimits and the left con extensions and whatever that you wind up using you can write in terms of these lower star and upper shriek, lower shriek and upper star maps. I think it's just a matter of convenience. Like I'm used to categories and functors and so on, and I like that I can just use them. But I think that I wouldn't make anything. I don't find practical value in making statements that are not well typed in the language that just has this these six functor formalism, right? It's so I don't know.
I totally agree with you. I totally like the parameterized. I mean well, what would you call the functor point of view? But the type family point of view to me is very clear. But I just wondered if you'd thought about you mentioned the Tom spectra work and how it was very valuable there. And I guess there must be some version of that that could be phrased where you actually do have a total space.
Yeah. I'm sure. Yes. I haven't done it, but I'm sure you can translate. Like, for example, the arguments in my paper with Toby. I mean, at some point we were really talking about quasi-categories, and there are individual simplices that get mentioned and so on. But that's only a tiny bit of it. I don't think it should be too difficult to redo that kind of thing in the theory of parameterized spectra. At least, yeah. No, maybe there is some advantage. I think it gives you, just thinking infinity categorically, gives you easier access to the entire hierarchy of types of monoidal structures, like En monoidal in infinity categories. I'm not in, so there should certainly exist a version of the theory of parameterized spectra that is sort of not strict. Maybe you could just redo it using infinity categories instead of categories where they're used, and that might make it easy to talk about En monoidal things. But I think maybe as is, it's really only practical to talk about E1 and E infinity. And right, so and I think this is consistent with the fact that several of our results in that paper were already known for E1 and E infinity, and just proved them for all En.
Nice.
Yeah. Maybe once you get into multiplicative structures, you would need sort of further development to be able to handle intermediate levels of commutativity. It's possible.
Okay, well, I think I've been talking long enough, and we're getting close to 1. So
yeah,
maybe.
I did have like one other question of the form. Should I be thinking about this more? That I wanted to pose to people. So my experience reading about homotopy type theory is usually that I read a definition of something that I'm already supposed to know, or a statement of a theorem that I'm already supposed to know. And first blush, it doesn't make any sense to me. And then I use the crutch of translating things into vibrations and then figure it out. It is what I knew about already. And but one place where this surprised me was in just describing a pushout, right? Instead of having 3 spaces with 2 maps between them, pushouts are often described with the 2 ends, the 2 legs of the pushout diagram, and then the dependently family of the fibers of the other 2 maps, right? The products of the fibers. And it's nice because it makes it look like a relation that you're quotienting the disjoint union by. I guess it is a relation that you're quotienting the disjoint union by, just the relation is not like the fibers of the relation are not all empty or contractible. They could be any type, right? But and so I translated into normal terms that it is a normal pushout. Any pushout expressible that way is easily expressible as what I think of as a normal pushout. But this is another thing where I'm wondering, should I be taking this point of
We're losing your connection a little bit. Yeah, you're still frozen for at least for me. Yeah, and Emily.
That what describes the pushout are the joint fiber.
Oh, we might have to end things unceremoniously. Oh, yeah, he's just reconnected. I see.
Sorry, Zoom crashed on me.
Oh, okay.
Yeah, well, it's late. Maybe I shouldn't push that question, but that's one thing I wondered about, whether, you know, this sort of more, it feels like it fits in with this question about, should I be thinking about these more dependently typed universal properties? This seems like a much more dependently typed way to describe a push-out diagram. And I'm not sure I see value in that yet.
I don't have a great answer to that question. I know that people like Egbert Reike and David Varen have made great use of thinking of these generalized relations and been able to get some sort of inductions going from that point of view. But yeah, I don't have a great answer.
All right.
Okay, on that note, let's thank Omar again.
No, thank you for the invitation.
Yeah, it's really nice to have you. And we're back in 2 weeks with the final talk of the term. So we'll see you all then.
Bye.
Thanks, Omar. Hi, Dan. Hi, Emily. Nice to see you all.
Hey, Martin.